Hello, welcome back to Astronomy. This is Chapter 15 on surveying the stars. In Chapter 14, you learned about the Sun and particularly the internal processes that go on inside it. And those processes take place inside all stars. So now we're going to zoom out beyond our solar system and look at all stars, particularly the ones that we observe in our galaxy. And this is Part 1 on stellar luminosity. Stars come in varieties of sizes, and if you look at this graph, here's the Sun down and to the left, but there are stars much larger than the Sun. These two stars, Aldebaran and Rigel, are called giant stars, but then there are supergiant stars like Antares and Betelgeuse. And not shown on this graph are stars that are much smaller than the Sun. In this chapter, we're going to look at the different sizes, the different colors, temperatures, all the differences between the stars. Astronomers classify stars based on two factors, luminosity and temperature. And in this video, we're going to look at stellar luminosities. Now, luminosity just means brightness. It's how much power, how much energy it's putting out. Part 2 video, we'll look at stellar temperatures. And then the Part 3 video will wrap it up as we look at a comparison between stellar luminosities and stellar temperatures. And we'll see what we learn about patterns in stars when we compare luminosities with temperatures. Let's think about stellar luminosity. A star has a certain amount of power that it gives off. We can measure that in watts. And it gives that power out in all directions into space. And then we on Earth get a little bit of that power. And so here you can see in this depiction, there's Earth and maybe that thing that the sunlight is falling on, that's a solar panel. So when we use solar energy, it's that little bit of sunlight that the star put out in all directions and that little bit that's hitting on the solar panel. And as we go through chapter 15, we're going to think about this variety of stars. Here you can see in this picture, the stars have different brightnesses. Some look brighter than others, some look dimmer than others. They have different colors. What you can't see directly is that they have different temperatures as well. The star's apparent brightness is how bright it looks to an observer, in that case to us on Earth. Now, whenever in science you see the word apparent, like apparent brightness, it has something to do with how it is perceived from the observer's point of view. So we talk about the apparent brightness as seen on Earth, but if you go somewhere across the galaxy, the sun, if you go far away from our solar system, for example, the sun is going to look not as bright. It's going to have a lower apparent brightness. Now, certainly if you move across the galaxy, nothing actually changes in the sun's power output. It's still got the same luminosity. But if you're far, far away, its apparent brightness will look different. The apparent brightness of a star depends on both distance and luminosity. And so I just described if you were to move far across the galaxy, the sun would look dimmer, and that has to do with distance. The closer you are to a source of light, whether it's a star or a flashlight, the closer you are, it will appear brighter to you. And also luminosity. The brighter the star is, the brighter it will look to you. I'll define luminosity as the amount of power that a star radiates each second. Now, power is measured in energy per time or energy per second, and it's measured in watts. So going back to this picture, luminosity is the total amount of power the star radiates into space. The apparent brightness is the amount of starlight reaching Earth. It's energy per second per square meter. Thought question. Alpha Centauri and the Sun have about the same luminosity. Which one appears brighter? And when I say appears brighter, it means appears brighter to us on Earth. Well, clearly the Sun is the answer. The Sun is by far the brightest looking star in the sky. because it's so much closer to us. Let's think about why apparent brightness diminishes with distance. If you think about this star in the center, it could be the sun or really any star, it's putting out luminosity. It's putting out a certain amount of power going in all directions. So if you imagine that energy that's going out in all directions, making a sphere, a bubble, an ever-increasing bubble that's moving outward at the speed of light. And it's like blowing up a balloon. The balloon, it starts out as small, but you put air into it, you blow it up, and it expands, it gets bigger and bigger. So the balloon gets bigger, but it's the same amount of balloon material. It just gets stretched thinner and thinner. So you've got the same amount of balloon material, but it's being spread out over a larger area. So there's not as much balloon material in a given square centimeter. And eventually, the balloon gets stretched so thin that it will pop. Well, this is what happens to light. You have a certain amount of energy that goes out, and here it's a sphere with a radius of 1 astronomical unit. And let's take this amount in this little square right here. That's a certain amount of light spread out over that square. Now, as the light goes out to 2 astronomical units, that same amount of light that was concentrated in 1 square, let's call it 1 square meter, is now spread out over 4 square meters. As the bubble of light gets larger, now the light is out to 3 astronomical units, that same amount of light is spread out over 9 square meters. And so it's like the balloon getting stretched thin. What was once an amount of light hitting 1 square meter is now spread out over 9 square meters, which means every individual square meter here is only getting 1/9 of the power as what it got over here. So the luminosity stays the same. It's just the brightness that the star puts out, but the apparent brightness gets dimmer as you get farther and farther away. Now the area of any one of these spheres is 4 pi times the radius squared. And when we divide the luminosity put out by the star by the area of that sphere, you get the apparent brightness. The relationship between apparent brightness and luminosity depends on distance. This is the formula that is very important in astronomy. It's very important in how we assess the brightness or luminosity of galaxies and stars, and it's also useful in assessing the distance to these various things. So here it is, apparent brightness, which remember is how bright it looks to the observer. And that is something that can be measured by an instrument called a photometer. It measures the apparent brightness, is equal to the luminosity divided by 4 pi times the distance squared. Now with the luminosity in the numerator of this fraction, that means that the brighter the star is, the brighter it's going to look. But distance in the denominator means the farther away it is, the dimmer it's going to look. And distance squared just means that as distance increases, brightness is affected greatly. It goes down pretty quickly. We can determine a star's luminosity if we can measure its distance and apparent brightness. So doing some algebra to the equation in the middle, we get luminosity is 4 pi times distance squared times apparent brightness. Now in this class, we're not going to be doing the math. We're not going to be plugging numbers into these formulas or directly using these formulas, but it is important to understand this general relationship here, that apparent brightness is luminosity divided by, you don't even need to remember that constant 4 pi. That's only necessary if you're actually plugging numbers into the calculator, but just know it is some constant times the distance squared down in the denominator. One more way we could express this equation is to solve it algebraically for distance. Distance is equal to some factor of luminosity divided by apparent brightness. And so there are 3 variables here: apparent brightness, luminosity, and distance. Using one form of this equation, if you know 2 of those variables, you can solve for the other variables. So if you know apparent brightness and luminosity, you can solve for the star's distance. If you know the star's luminosity and distance, you can solve for the star's apparent brightness. So sometimes in astronomy, we're solving for one thing, like distance. Sometimes we're solving for another thing, such as luminosity. We can think about how far away are these stars? What are the distances to these stars? And that's important because if we're going to use the equation that I showed on the previous slide, then we need to know their distance. So how do we assess the distances to these stars? There is something called parallax, and it's the apparent shift in position of a nearby object against a background of more distant objects. So if you hold your thumb up in front of your face and you look at it through your left eye and then through your right eye, and then shift between left eye and right eye, your thumb will seem to shift back and forth between right and left. It's shifting relative to the background of more distant objects. Maybe it's the wall across the room or something like that. How much it shifts has to do with how close your thumb is up to your face. So if you hold your thumb a few feet away from your face and you go left eye, right eye, keep shifting between your eyes, your thumb has a little bit of shift to it. If you bring your thumb up real close to your nose, go left eye, right eye, look at it through each eye alternately, your thumb will look like it's shifting across the room. So the closer it is to your face, the larger the shift. Well, we use this concept called parallax when looking at the distances, not of your thumb, but of a star. Apparent positions of nearest stars shift by about 1 arc second. And so remember, an arc second is 1 over 3600 of a degree. But what's the analogy to left eye and right eye? Well, as the Earth moves around the sun, picture where the Earth is in January and then in July. Those are two different positions from which to view stars. And just like when you're holding your thumb in front of your face, as you shift between left eye and right eye, well, we observe stars between January and July, and there's a very, very small shift. In fact, as I wrote here, for the nearest stars, it's less than 1 arc second. The parallax angle depends on the distance. Parallax is measured by comparing snapshots taken at different times and measuring the shift in the angle to a star. So here you can see in this diagram, not to scale, the Earth on one side of the sun, on the other side of the sun, and here we're looking at a particular star. And from the point of view when we're looking at July, the star looks like it's over here. From the point of view looking at in January, the star looks like it's over here. Now, this is a very squished, not to scale diagram. The reality is that the stars don't shift that much. As I said, even the closest stars only shift by not even 1 arc second. But we have very precise instruments that can measure very small shifts. The farther away an object's distance, the smaller the parallax angle. Current technology allows astronomers to use this method to measure distances to stars up to about 1,000 light years away. So this method is called stellar parallax, using parallax to measure distances to stars. It's important to note that there is a limitation. Given our current technology, it's good out to about 1,000 light years. Now, just the Milky Way galaxy alone is 100,000 light years in diameter. So 1,000 light years doesn't take you very far across the galaxy. But within 1,000 light years of us in all directions, we have tens of thousands, maybe even hundreds of thousands of stars that we can accurately use this method to measure their distance from us. Here is a measure of distance that I'd like you to know. It's called a parsec, and parsec is short for parallax second. It's the distance that a star is from us if it has a parallax shift of exactly 1 arc second. And actually, there is no star that is this close to us, but it is a convenient unit for measuring. No star is this close to us. In fact, the closest star, Proxima Centauri, is about 4.2 light years away. And so its parallax angle is less than an arcsecond. And all stars except the sun have a parallax shift of less than 1 arcsecond. And you should know that a parsec is 3.26 light years. And sometimes for convenience, astronomers, or maybe you're reading in astronomical literature, sometimes they use light years. I prefer to use light years, but sometimes other astronomers will use parsecs. Parsec is 3.26 light years. So it's kind of like some people having a preference of using inches and some people using a preference of centimeters. They're both valid units for measuring distance. There is great diversity in the luminosity of stars. The brightest stars are about 1,000,000 solar luminosities. Now look at this notation that I wrote. 10 to the sixth power, that's 1,000,000, a 1 with 6 zeros after it. Capital L, that stands for luminosity, and the subscript is sun. So that's a short way of saying solar luminosities, meaning the brightness of the sun. We usually don't talk about the brightness of stars in watts, because then we'd be using unit numbers like 10 to the 26th and 10 to the 27th, these mind-bogglingly large numbers. And it's more convenient to compare them all to one standard, so we compare them to the sun. So the brightest stars are about 1,000,000 times as bright as the sun. The least luminous stars, the dimmest stars, are about 10 to the negative 4 times the luminosity of the sun. So 0.0001, otherwise you can think of that as 1% of 1% of the sun's brightness. I want to now talk to you about the magnitude scale that we use to talk about the apparent brightness of stars, not only stars, but we can also use it for planets, comets, galaxies, anything that is up in the sky. And it started with Hipparchus, who lived from about 190 to 120 BC. He was a Greek astronomer who cataloged the stars in the sky according to their brightness. So in his catalog of stars, he took the brightest stars and he called those first magnitude stars. Now keep in mind, when I say the brightest stars, they were the brightest stars from Earth's perspective, and actually as he determined by his own eyes what was the brightest. This has nothing to do with him cataloging stars by their actual luminosity, because he had no way of knowing how bright those stars actually were, but rather how bright they look to us on Earth. Those that were not quite as bright as first magnitude stars, kind of second place stars, they were second magnitude. And then there was third magnitude, fourth, fifth, and the very dimmest stars, the stars that Hipparchus could barely see, were sixth magnitude stars. So every star had a number, either 1, 2, 3, 4, 5, or 6, 1's being the brightest, 6 being the dimmest. It's important to understand that the lower the number, the brighter the star. This was one way of describing apparent brightness of stars, and we call this apparent magnitude. Today, the system has been more precisely mathematically defined. Rather than simply 6 categories, 1, 2, 3, 4, 5, or 6, it's actually now a numerical measurement of a star's apparent brightness. So there's a formula that I won't give in this video, but there's a formula that determines what exactly the magnitude is. As I said a minute ago, it's important to understand that just like in Hipparchus's system, the lower the magnitude, the brighter the star. So for example, Rigel has a magnitude of 0.14. Polaris, the North Star, is 1.97. And so just based on those numbers, the lower number, Rigel, means it's brighter than Polaris. Test yourself. Here are 3 stars with their magnitudes. List them in order from brightest to dimmest. So as you're thinking about what is the brightest star here, look for the lowest number. And that's going to be 0.34, which is Procyon. And then Aldebaran with 0.87. And finally, the largest number, meaning the dimmest star, is Alpha Centauri b. On the magnitude scale, a magnitude of 0 is an arbitrarily defined brightness. So 0 magnitude does not mean 0 anything, 0 brightness. In fact, a 0 magnitude star would be a very bright star. Stars can have negative magnitudes, and that has nothing to do with negative brightness. It just means that they are brighter than 0 magnitude stars. For example, the brightest star in the sky, other than the sun, is Sirius, the dog star. It has a magnitude of negative 1.46. Astronomers measure more than just stars with the magnitude system. It's a convenient way to describe the brightness of planets, asteroids, and galaxies. The brightness of the planets, or their apparent brightness, changes month by month as different planets go around the solar system. Sometimes we're on one side of the sun, sometimes on the other. However, this is just a sample of the planets' magnitudes from April 2020. Venus had a magnitude of negative 4.4. And generally, Venus is always about negative 4. And that means it's brighter than the brightest star. Again, I'm excluding the sun from that. It's brighter than Sirius, much brighter. Jupiter is also very bright, and at least in April 2020, it had a magnitude of negative 2.2. And generally, Jupiter is usually about negative 2. So Venus and Jupiter are brighter than the brightest stars, and Venus is significantly closer than Jupiter. Other planets, you have Mercury, negative 0.1, Saturn, positive 0.6, Mars, 0.7. And those are the 5 planets that were known about since ancient times: Mercury, Venus, Mars, Jupiter, and Saturn. Then you get into planets that were only discovered after the invention of telescopes. So Uranus was at about 5.9. I wrote that it's too dim to see without a telescope. It's barely on the edge of visibility. If you're in a very dark sky with no light pollution and good eyesight, you might be able to see Uranus just barely with the naked eye. But for practical purposes, you need binoculars or a telescope to see Uranus. Neptune is at 8.0, which means it's way too dim to see with the naked eye. You definitely need a telescope for that. Test yourself. A star's luminosity is the A, apparent brightness of the star in our sky, B, surface temperature of the star, C, lifetime of the star, D, total amount of light that the star will radiate over its entire lifetime, E, total amount of light that the star radiates each second. What do you think? Well, we can eliminate answer A because luminosity is not apparent anything. It is a true value. It has nothing to do with how we perceive it. B, I haven't even talked about surface temperatures, so it can't be that. C, I have not addressed yet lifetimes of stars, so we can eliminate A, B, and C. D is getting close to the answer. The light that the star radiates, okay, we're getting somewhere, but over its entire lifetime, nope, that's not it. The answer is E, the total amount of light that the star radiates each second. And luminosity is actually the same as power. Test yourself. A parsec is which one of these? A unit of luminosity, distance, time, or brightness? It is a unit of distance, just like a light year, and in fact, 1 parsec is about 3.26 light years. That is the end of part 1 of chapter 15. In part 2, we'll investigate the temperatures of stars. Have a great day.